Hello and welcome back to part 2 of this lecture series on convolutional neural networks. In the previous lecture, an overview of CNNs was provided, and we also observed in the previous video what is the effect of convolution on the dimensions of the image or the input data that is fed into the convolutional layer of the convolutional neural network. In this video, we will briefly discuss about the most common applications of CNNs, which we had touched upon on the previous lecture as well. However, the main focus of this video will be on the convolution operation itself. So what is the mathematical procedure that is being performed when we apply an input image to a convolutional layer wherein the input image is convolved with some filter and that produces an output image or output data. And so we will see in this video what is the operation of convolution and how it is performed between the input and the filter that is operating upon that input signal. So let us look at the major applications of CNNs. And one of the application of interest in the contemporary age is in the area of computer vision. So computer vision is basically the attempt to mimic the human vision system by a computer system. And as we see, the human eye captures images and our brain interprets the content of the image. So when we see something through our eye, that image information is interpreted by the visual area of our brain, and through that we understand that image as to what is the content of the image. And similarly, the objective of computer vision is to develop a system that can capture an image through a camera or any image sensing device for that matter, and then interpret the content of that image through some interpreting device, which could be a computer or a mobile phone or any edge device which is running the computer vision algorithms to process that input image and identify what is the content of that input image. So the idea of images can be extended to videos as well, because videos can be thought of as uh, a stream of images. So CNN has major applications in the areas of computer vision, which can involve object detection and object classification, or face recognition or face detection, which all come under the category of computer vision applications. So let us do a quick recap of the CNN architecture that we have seen in the previous lecture. And as we see from this image here, the input data or the input image is passing through each layer of the convolutional neural network. And the focus of the previous lecture was mainly on how the dimensions of the data is being altered as it passes through each convolutional layer. And clearly, what was the observation that we had when we pass an image from one layer to the other through the convolutional neural network? So basically, what we notice from these dimension information here is that the dimensions in terms of the width and height of the image, they become smaller and smaller as the image passes through each of the convolutional layers. So in the input image, the width is 39 pixels and the height is 39 pixels. At the output of the first convolutional layer, the width is 37 pixels and the height is also 37 pixels. In the subsequent layer, the 37 by 37 width and height is reduced to 17 by 17 and then subsequently to 7 by 7 and so on. So overall, the observation that we see is that the width and height of the image becomes smaller as the image passes through the convolutional layers. The other observation that we see is that the depth of the image, which is the number of channels that are present in the image, that increases as the image passes through the convolutional layers. So the input image had 3 channels to start with, and at the output of the first convolutional layer, the number of channels has become 10. and in the output of the second convolutional layer, the 10 channels has been converted to 20 channels, and then in the subsequent layer that has become 40 channels. So basically what we see is that the width and height becomes smaller and smaller as the input image passes through the convolutional layers, and the depth of the image, that is the number of channels, increases as it passes through the convolutional layers. And we talked at length about the relationship between the dimensions of the input and output in the previous lecture. We will touch upon that in today's lecture, as well as we see an illustration of how the convolution is performed. But this is something that we need to remember, because a lot of the processes that are done is based on these facts that the image dimensions become smaller in terms of width and height, and the depth becomes bigger. So these are the two observations that we see when we pass an input image through the convolutional neural network. So the question for today's lecture that we will attempt to answer is, what is the operation that is performed by each of the convolutional layers? So in this particular illustration here, we have three convolutional layers which process an input image by convolving the input with some filter. So we will try to understand what is the operation that is performed by the convolutional layers. Now, as the name suggests, these are convolutional layers, so the operation that is performed is indeed convolution. So let us try to understand in depth what is the convolution operation and how it is computed between the input image and the filter that is operating upon that input image. So let's delve a bit deeper into the convolution operation and try to get an understanding of the computation that is involved in the convolution process. So here we have an input image, and for simplicity, we are considering an input image with a single channel. So it is having a depth of 1. So it's a one channel image. And the dimensions of this image is 6 by 6. So width is 6 pixels and the height is 6 pixels, as you can see here. And we are going to convolve this input image with some filter of some size. In this case, we are taking a filter of size 3 by 3. Now, the size of the filter in terms of width and height can be anything. It does not have to be the same 6 by 6, but of course the number of channels in the filter must be the same as the number of channels in the input image. So in this particular case, since the input image is having a single channel, the filter is also having a single channel. That means it is a single matrix of filter elements which are going to be convolved with the input image. So now, how do we perform the convolution operation? So what we do is we use a window which has the same dimensions as that of the filter. So the filter is 3 by 3. So we use a window of size 3 by 3. So the window is highlighted in red over here. So that's the window which has the same size as the filter. Now, to perform the convolution between the elements within that window and the filter, we perform an element by element multiplication of each of the pixels within that window with the corresponding elements in the filter, and then add up all those products. So that's 3 into 1 plus 0 into 0 plus 1 into minus 1, which is what is illustrated here. 3 into 1 plus 0 into 0 plus 1 into minus 1. Plus we go to the second row of the window. The element in the image is 1 and the element in the filter here is 1. So that's 1 into 1 plus 5 into 0 plus 8 into minus 1. And similarly for the third row, it is 2 into 1 plus 7 into 0 plus 2 into minus 1. So when we multiply each of these pixels element by element with the filter and then add up all those products, whatever result we get, that becomes the value of the output pixel corresponding to that window. So that's the first pixel in the output that we get. And again, the output size here is going to be 4 by 4. Again, this is something that we have discussed in the previous lecture. What is the relationship between the input image, the filter, and the output image? So I will illustrate that later in subsequent slides as well. But for now, let us consider that the output is indeed going to be a 4 by 4 image. So the first pixel of the output image is obtained by multiplying these elements within the window with the corresponding elements of the filter and adding up those products, and we get -5 as the answer for that. So the first pixel of the output is -5. And then what we do is for the to calculate the next element in the second position here of row 1, so column 2 row 1, so which is this position which I'm pointing out here, to compute that pixel value in the output, we have to shift this window, which is highlighted in red, by 1 pixel to the right. So we are going to shift it 1 pixel to the right. So now the window has moved 1 position to the right. So we have now the pixels within that window, and we are going to multiply them element by element with the elements of the filter and add up those products, and that results in an answer of -4. So we get this -4 as the second pixel value for the output image. Now, if you look at this bottom matrix here that I've illustrated, it is not 0 power 1 and 1 power 0, no. It is just a superposition of the pixel values in the window of the input image and the values of the filter. So we have in the image, the window of the image, which is 0, 1, 2, 5, 8, 9, 7, 2, 5. We have put that here, 0, 1, 2, 5, 8, 9, and 7, 2, and 5, which are the elements within that window of the input image. And then the elements of the filter, which is 1, 0, -1, 1, 0, -1, 1, 0, 1, -1. It is just superimposed 1, 0, -1, 1, 0, -1, 1, 0, -1. And we simply multiply those terms. 0 into 1 plus 1 into 0 plus 2 into -1 plus 5 into 1 plus 8 into 0 plus 9 into -1 plus 7 into 1 plus 2 into 0 plus 5 into -1, and we get the answer -4, which is the value of the second pixel in that position over here. So don't have a misunderstanding that it is 0 power 1 or 1 power 0 or 2 power -1. These are just the values of the input image pixels and the values of the filter that are superimposed into the same boxes. So it is not power, but it is basically the elements superimposed within the same box, and we basically perform an element by element multiplication of those numbers and add them all together to compute the output pixel value, okay, which in this case for the second pixel is -4. And we keep repeating this process by shifting the window by 1 pixel each time, and this amount of shift that we perform on the window, this is called as the stride. So in this case the shift is by 1 pixel, so we call the stride, and it is denoted by the letter S, and the stride value is equal to 1 in this particular illustration because we are using the window which is shifted by 1 pixel each time. So to compute the next pixel value, we will stride the window by 1 pixel to the right. So it has moved 1 pixel to the right now. So we get the elements of the window here, which will be multiplied element by element with the filter values, and then those products will be added together, and that result becomes the pixel value of the output image, which in this case is 0. And we shift it one more time, and that gives us the fourth pixel value. So as we slide through this, we have now reached the edge of the image, so this window cannot be shifted any further, so we get only 4 columns of pixels for this particular case. Now that we have reached the right edge of the image, the window has reached the right edge of the image, the next step is to bring it back to the left edge and shift it 1 pixel down. So in that case we will end up in this situation. So we have brought it back to the left edge and shifted it down by 1 pixel, and that gives us the value of the output image for the second row, the first element of the second row. Again, the process is the same. where we multiply the elements of the window with the elements of the filter element by element, and then add up those products, and whatever is the result of that, that becomes the output pixel value, which in this case is -10. And we'll keep doing this by shifting or striding the window forward to the right, and then subsequently down 1 pixel, and we'll repeat the process until we reach the bottom right, or the window reaches the bottom right corner of the input image. Excuse me. So we'll move on to the next pixel or the next window, and that will result in the output value for the next pixel. And when we keep doing this, eventually we will have computed all the pixel values of the image until we have reached the bottom right corner of the input image. So the window is now at the bottom right corner of the input image, and each time the process is the same. The elements of the window are multiplied with the elements of the filter element by element, and those products are added together, and that gives us the corresponding pixel value for the output image. So now we have got a 4x4 output image whose pixel values are given by these numbers, which we saw how to compute by multiplying the window elements with the filter elements element by element, and then adding up those products. Okay, so now we have a clear understanding of how the convolution operation is performed between the input image and a filter, and we have done this illustration now with a stride value of 1. So the window is shifted by 1 pixel value each time to compute the subsequent or the next pixel value of the output. Let us now look at the relationship between the dimensions of the input, the filter, and the output. Of course, we took the output size to be 4x4. Let us see what is the relationship between the input image, the filter size, and the output image. So the input image in this case is 6x6. The filter size is 3x3. So the input image we denote by the letter n. So that's n by n, which is 6x6. So n equals 6. The filter size is f by f. So the size of f is 3. And the output dimension is given by this expression, which is n minus f divided by s plus 1. So n in this case is 6. So it's 6 minus 3 divided by the stride value, which is 1. So 6 minus 3 is 3. Divided by 1 is 3 plus 1. So 3 plus 1 is 4. So we get the width as 4. And the height is also given by the same expression. So that's 4x4. So we get an output of size 4x4. And we have seen how to compute the output pixel value for each location of the output pixels by multiplying the elements of the window of the input image with the filter elements and adding up those products. So we got a 4x4 output. Of course, there is another parameter on which the output size depends, and that is called as the padding. Again, we will illustrate what is padding towards the end of today's lecture. But now we have seen how the output size is affected when the stride is equal to 1. Let us now see what happens if we increase the value of the stride. Rather than shifting the window by 1 pixel each time, what happens if we shift the window with more than 1 pixel, say 2 pixels or 3 pixels? What would be the dimensions of the output image, and how do we compute the output pixel values? So one of the variations that can be done in the convolution operation is to change the size of the stride. So when we have a stride of 3, what we notice is that the output image is even smaller. Rather than a 4x4 output image, we get a 2x2 output image. So when we perform the same convolution between the same input image and the same filter, but now with a stride of 3, the stride of 3 means that this window, which is highlighted in red, after computing the first element, it is shifted by 3 pixels to the right, and then subsequently 3 pixels down, and so on. So in that case, we end up with getting a much smaller image. So this is the output value that we get for the first output pixel. So basically we start with the window of the input pixels, multiply them element by element with the filter values and add those products, and of course it is the same as what we saw in the previous case. We get it as -5. But now instead of shifting this window by 1 pixel to the right, we are going to shift it directly 3 pixels to the right. So when we shift it 3 pixels to the right, that window moves right over here to the right edge of the input image. So it was the window was starting here. Now it has moved 1, 2, 3 pixels to the right. So the window is over here now. So with this windowed pixels, we multiply them element by element with the filter and add those products, and that gives us the subsequent pixel value for the output. So of course, there is no further shift possible for this window to the right. So therefore, we have to bring it back to the left and move down by the stride value. So when we move down by the stride value after bringing this window to the left, so the window is now at the bottom left corner of the input image in this particular case. And again, we multiply these window elements with the filter elements element by element and add those products, and we get a value of -3. And we shift the window now to the right by 3 pixels because the stride value is 3, and that gives us now the output pixel, which is -16 in this particular case. So the process is the same, except that the stride of the window is now 3 steps each time. So now having a larger stride size helps reduce the size of the input image in terms of its width and height even further. Previously, with the stride of 1, the 6x6 input image became a 4x4 input image. But now with the stride of 3, the output image is 2x2 for the same size of the input image and the same size of the filter. All we have done is change the stride value from 1 to 3. So now, including the stride value, again, the expression for the output dimension is n minus f by s plus 1. So n is still the same as before, which is 6. And the filter size is still 3. But now the stride value s is 3. So it is 6 minus 3 divided by 3. So s is 3. So 6 minus 3 is 3. 3 by 3 is 1. And 1 plus 1 becomes 2. So the width is 2, and similarly the height is also 2. So the output dimension is now 2 by 2 image. So this is what we have got, and the procedure for the convolution remains the same. We simply multiply the elements of the window of the input image with the filter elements in an element by element manner and add up those products. Okay, so what we observe here is that increasing the value of the stride s to a larger number reduces the size of the image even further. So now that we have a clear understanding of how to perform convolution on an input image that has a single channel, let us extend the idea to understand how convolution is performed when the input image is having multiple channels. So let us take an example of an input image that has 3 channels. We have the red channel, the green channel, and the blue channel. So it's basically a color image with the 3 channels RGB, red, green, and blue. And we are going to perform convolution of this 6x6 input image, which has 3 channels with a filter of size 3x3. And as before, when we perform convolution, the depth of the filter, that is the number of channels of the filter, must be the same as the number of channels of the input image. So since we have 3 channels in the input image, our filter must also have 3 channels. So we have a 3x3x3 filter. So it's a filter with 3 channels, which I have highlighted in pink, gray, and yellow or orange here. So the pink is the first channel of the filter, the gray is the second channel of the filter, and the orange shaded one is the third channel of the filter. And we are going to perform convolution with a stride of 3, and the process is pretty much the same as we have done it for a single channel. Basically, we start with a window of pixels for each of the channels. So the red channel has a 3 by 3 window, which is the same size as the size of the filter, which is 3 by 3. So the elements in the window for the red channel are multiplied with the elements of the filter's first channel, element by element, and they are added together. So these elements 301, 158, 272 are multiplied with 10 minus 1, 10 minus 1, 10 minus 1, which is what is illustrated here. So 3 into 1 plus 0 into 0 plus 1 into minus 1 plus 1 into 1 plus 5 into 0 plus 8 into minus 1 plus 2 into 1 plus 7 into 0 plus 2 into minus 1, and that will result in minus 5. Now, for the sake of simplicity and for the sake of this illustration, I have considered that the green channel as well as the blue channel, they all have the same pixel values as in the red channel. So the same numbers are being utilized in the green channel as well as in the blue channel. And similarly, the second and third channels of the filter are also having the same values as the first channel of the filter. So we are using the same numbers. So when we perform the convolution between the window elements of the green channel with the second channel, which is the gray elements of this of the filter, then we multiply the second channel elements which are within that window with the corresponding elements of the second channel of the filter. And since we are using the same numbers as the first channel, and since the product is going to be the same, we get the same answer, which is minus 5 in this case. So the product, the element by element product, and the sum of those products for the particular window is still going to be minus 5 for the second channel as well. And similarly for the third channel, we will get the same answer of minus 5 because we have used the same pixel values for all the three channels and the same filter element values for all the three filters in the filter for each of the channels of the filter. So now once we have performed the element by element multiplication of that particular channel, so we get the output for that channel, and then what we do is we combine the outputs of the three channels by adding them together. So the output of the first channel is minus 5, the output of the second channel is also minus 5, and the output of the third channel is also minus 5. We add them all together and we get minus 15. So that becomes the first element of the output image, which is in this case minus 15. So basically, when we have multiple channels, we perform the convolution operation as before on each channel individually, and we combine the outputs of all the channels by adding the results together. So we get, in this case, minus 15. And in this way, we can proceed by shifting this window based on the size of the stride. So if we stride it by 3 pixels, so the window here will come to the top right corner of each of the channels, and those elements, the 3 by 3 dimension elements of the top right corner will be multiplied with the corresponding filter elements, and those products will be added up to get the output of the individual channels, and the three outputs of the three channels will then be added together to get the subsequent output for the next pixel element of the output. So that way we will have our 4 pixels for the output, which is for the first window, which is the top left, the second window, which is the top right, excuse me, and the third window, which will be the bottom left corner of the input image, and the fourth window will be the bottom right corner of the input image. So for the stride of 3, we will end up getting a 2 by 2 output image, and the output image now has only a single channel. Why? Because we are using only one filter for the output. There is a single filter but 3 channels. So the filter is defined by the elements in this particular filter matrix. So we have a 3 by 3 filter with 3 channels, but it is a single filter. Since the number of filters is 1, the output has only one channel. So if you recall from the previous case, the for stride of 3, we got the first pixel value as -5, the second pixel value as 8, the third pixel value as -3, and the fourth pixel value as -16. Now, since we have three channels, and since we have used the same pixel values for all the three channels and the same filter values for all the three channels of the filter as well, so each of the channels will give an output of -5. Combining the -5 three times, or adding it three times, gives us -15. Similarly, adding the 8 three times will give us 24. Adding the -3 three times will give us -9. And the -16 added up three times will give us -48. So we have seen now how to perform the convolution between the input image and the filter when the number of channels is anything other than one. Of course, one thing we need to remember here when we are performing the convolution is that the number of channels in the filter must be the same as the number of channels in the input image. And the depth of the output image will depend on how many filters we are using. So this is a single filter with three channels, and because it's a single filter, we have a depth of 1, or the output image is having a single channel. Excuse me. Okay, now that we have seen convolution for the single channel case as well as the multiple channel case, let us see now what are some of the drawbacks of the convolution operation and how those drawbacks can be addressed to remove the deficiencies of the convolution operation. One of the problems that we notice is that the operation of convolution causes the dimensions of the image to shrink. So the 6x6 input image is reduced to a 4x4 output image. So the dimension of the image is shrinking because of convolution. And the other aspect that we notice is that when we shift the window by a stride of 1 or by a stride of any other number other than 1 as well, what we notice is that the pixel values which are at the corners, they are being utilized fewer number of times in the computation of the convolution as compared to the elements which are in the middle, because as the window shifts one pixel to the right, the elements in the middle are used multiple times in the convolution operation, whereas the elements in the corners are used only a fewer number of times. So this results in some loss of information and of the pixel values which are in the corners of the input image. So to avoid this, we need to have some solution to deal with these two drawbacks. How can we avoid the problem of shrinking of the output image as compared to the input image? And how can we also make sure that the pixels in the corners of the image are used more often, more number of times in the convolution operation? And the solution to this is by what is called as the padding operation. So if you see this, when we go from, when we shift the window, the window overlaps with the middle elements more number of times as compared to the corner elements. So how do we address this issue? And the solution is to pad the input image with some additional pixels around it. And in this particular case, we have padded the input image with 0. So this is called as zero padding. Of course, there are other kinds of padding as well, which we'll touch upon at some later stage. But for now, let us just understand that padding is a process in which the input image, which is shown by these black pixel values, is surrounded with some additional pixel values which are highlighted in red values. In this case, we are assigning the values of 0 to each of those pixels surrounding the actual image. So that way the size of the input image is increased. Again, padding is something that we briefly touched upon in our first video, but today we are going to see discuss padding in the context of how padding overcomes the drawbacks of convolution. So we have padded the input image with a single layer of pixels. So we say that the padding is one layer, and in this case it is zero padding because we have assigned a pixel value of 0 to all the padded pixels. So now what happens is the original image size, which is 6 by 6, that is n equal to 6, is padded with 1 pixel all around it. So that results in an image, the padded image, which is now 8 by 8. So if we count the number of pixels in the width and the height, it is now 8 pixels along the width and 8 pixels along the height. So it's now become an 8 by 8 input image. And now what happens is with these dimensions, what would be the dimension of the output image? The expression for the output dimension in this case is n plus 2p minus f divided by s, where p is the number of pixels that are added around this image. So in this case, the p is equal to 1, n is equal to 6, and the stride value, I'm going to consider it as 1. So the stride is 1. And substituting all the numbers, we get n is 6 plus 2 times p, 2 into 1 is 2, minus f, f is the filter size, which is 3, divided by the stride, so stride is 1, so 6 plus 2 is 8, minus 3 is 5, 5 divided by 1 is 5, and plus 1, that is 6. And similarly for the height, it is also 6, so we end up with an output image which is 6 by 6. So the original input image is 6 by 6. And after convolution, the output image is also 6 by 6. And therefore, what we notice is that the first drawback of convolution, which was the shrinking of the image as a result of convolution, has been avoided. So we started with the 6 by 6 input image, and we still get an output image which is 6 by 6. So the first problem has been addressed. And the second issue, which is the corner pixels not being utilized more often, because we have padded the image with some additional pixels all around it, that means the corner pixels have been pushed inside or inward of the image. So that now makes the corner pixels being utilized more number of times in the convolution operation. So as we shift this window by 1 pixel each time to the right, so this corner pixel 3, previously it was being used only in a single computation. Now it will be used in more than one computation. In this case, it will be 2 computations and so on. So basically, by padding, the corner pixels are moved inward, resulting in those pixels being used more often in the computation of the convolution process. So that way, the second drawback of convolution is also addressed as a result of using padding. So padding is used for these 2 purposes: to keep the dimensions of the output image to be the same as the dimensions of the input image in terms of the width and height, and also to make the utilization of the corner pixel values more often in the convolution process. Now, when we want to have a certain dimension for the output, we can determine how much of padding is required for a given input image and for a given filter size. So we know what is the expression for the dimensions of the output, which is n plus 2p minus f divided by s plus 1. In this case, I'm choosing s equal to 1. So all we have to do is to find out how much of padding is required. We have to simply equate the output dimension with the input dimension. So the output dimension is given by this expression, n plus 2p minus f divided by s plus 1, and we have to equate that with the input dimension n, which is in this case equal to 6, right? So by equating this and solving for the parameter p, that will give us what should be the number of pixels that are to be padded for a given condition. For example, if we want to have the output dimension to be the same as the input dimension, so the input dimension is 6 by 6, so in this case n equal to 6, we want the output dimension to be the same n by n, which is 6 by 6. So we have to basically equate the output dimension with the input dimension. So we equate n plus 2p minus f plus 1 to be equal to n, and then we solve for p. So n and n on both sides will cancel out. So we end up with getting 2p minus f plus 1 equal to 1. So we just shift everything else to the right side by keeping p on the left, and that gives us a relationship between the filter size and the number of padding pixels that are required. So p is basically f minus 1 divided by 2. So in this case, the filter size is 3. So 3 minus 1 is 2. 2 divided by 2 is 1. So that means we need a padding of 1 pixel width all around the image. So that is why by using a single pixel of padding, we have obtained the output dimension to be the same as the input dimension. So we have seen in this video what is the operation or the process of performing convolution in a convolutional neural network. What is the computation that is involved between the input image and the filter to produce the output image, and we have seen in detail what is the procedure that is involved. So basically we take a window of elements in the input pixel and multiply them element by element with the elements of the filter, and then add up those products, and that gives us the pixel value of the corresponding location in the output image. And we keep repeating this process by shifting or striding the window across the entire input image and computing the value of the output pixel values each time. So I hope that this has given us a clear understanding of what is the convolution process that is being performed by each of the convolutional layers in a convolutional neural network. So we have delved into the convolution operation, and hopefully we have now a clear understanding of how convolution is performed. We have seen examples of convolution for different parameters in terms of the number of channels in the input image, as well as for different values of the stride, in terms of the stride, that is the shifting of the window that is used for the convolution operation. And we also saw what is padding and why padding is required. And so now we should have a fair understanding of how the various parameters affect the output of convolution, and also a very clear understanding of what is the process that is happening in the convolution operation. Of course, we also discussed about some of the drawbacks of convolution and how these drawbacks can be overcome by using padding. So congratulations, we have gone one step further into understanding convolutional neural networks in a better way. We will continue this discussion in subsequent lectures in this series, where we'll talk about the further details of the convolution operation and the additional operations that are performed within the convolutional neural network. What are the purposes of those operations, and how different features of the input image are extracted by performing these convolution operations. So we'll stop here for today, and congratulations once again for staying along and making an attempt to learn and have a better understanding of convolutional neural networks. And hopefully by the end of the series we'll have a clear understanding of how CNNs work, what is the convolution operation, and the implementation process of CNNs as well, and how the various features of an input image are extracted and used for classification and prediction purposes in convolutional neural networks.